Test. Let me know if you can hear me. Okay, good. Thank you. All right, good evening. Let's get on with our lecture. Hey, I guess, welcome back from the break. So we'll continue on the triple integral as we have started from the previous week. We started the triple integrals. Let's do a little bit of review. Basically, we started the triple integral in Cartesian coordinates. Okay. So this is the writing of triple integral. You are given a region D. Apparently, this is different from region R. For the double integral, it's a flat. This is a region D, it's a 3D space. And then what the triple integral is all about is to integrate certain function f, which is defined over this region D. Okay. So you integrate this function over region D. Right? So we got to make sure that this function is defined over this D. Define basically means you pick any point within this region D, you plug it into the function f, you'll get a value. Okay. If you get an infinite, that means this function is actually not defined in region D, so you actually cannot integrate. Right? But we'll make assumption all of our double and triple integrals will be a function that's defined over the region D. So in terms of computation, we have learned, right? Calculate in Cartesian coordinates. So what that involves is how do you find this dv, right? You can write it as dx, dy, dz, or any combinations. Right, there are 9 of them. So that involves finding the limits for each one of the coordinates. Okay. So if you recall the procedure is to determine the order of integration first. And once you get that nailed down, then you need to sketch the shadow of the region, right? In the last two, in the coordinates or the plane of the last two variables. So if you decide to do Z first, then you need to find a shadow within XY plane, because that shadow will give you the limits for XY variable. Right? So that's Cartesian coordinates. And then we also looked at the so-called cylindrical coordinates. So this is where we're going to continue today. Cylindrical coordinates basically means you have a set of coordinates which is defined as r theta z. If you got the point P at here, you can certainly describe the point P using x, y, z. That's the Cartesian coordinates. And you can also describe the point P using r theta z. So the definition for r is that if you project the point P into the xy plane, then this is your r, and this is your theta. So r and theta is basically the polar coordinates, right, in 2D. And this is your z. Okay. So that's cylindrical coordinates. As I illustrated, you can consider yourself like you have a cylindrical coordinates attached at this point P. Okay. Right, there are 3 unit vectors that are here. This unit vector points to the direction of r. Okay, that's a reading direction. And this unit vector points to the direction of a theta rotation. So that's always perpendicular, right, to the r. And this direction points to the positive z-axis direction. So the 3 unit vectors here satisfy the right-hand rule, and they are in analogy to the I hat, J hat, and the K hat. Right. So these three coordinates, or the coordinates here, cylindrical coordinates, right? As you can see, it's moving as a P at a different location. Then you have a basically changing coordinate system, right? Not like this X, Y, Z. It's a reference frame. And we also have demonstrated, right? If I decide to use cylindrical coordinates, then the triple integral at here, okay? So the triple integral will become, so X, first of all, X can be reduced to R cosine theta, Y is R sine theta, and Z is still Z. Okay? That's the connection between cylindrical coordinates and Cartesian coordinates. So if you integrate your f function within the region D using cylindrical, then we need to replace the x with r cosine, replace the y with r sine. Z, you don't need to do anything, just keep it as z. And then it's dv, okay, that is changed to r. Okay, so technically we write dz first, then r dr d theta. Okay, so we write the r over here. Okay, and then the dz dr d theta. The reason I pointed out in the previous lecture is this is basically the order of integration for cylindrical. 99% of the time you will integrate using dz first and then dr d theta. Okay, not that you cannot do the other orders, but this is proven to be more intuitive and also easy to accept. Okay, to find the limits, right? Now the addition r at here is due to the Jacobian calculation. And if you calculate using a different approach in the lecture notes, you can get the same r here, right? So basically, in cylindrical coordinates, this will be your formula, okay, for calculating the triple integral. Okay, so today we're going to look at some examples. How do we find the limits for z, for r, and for theta, okay, using cylindrical coordinates? Now, before I proceed with the example, I just want to maybe reinforce this cylindrical coordinates a little bit, okay, before we look at a concrete example here. Okay. So let's call this as some sort of a commons here. Okay. Okay. So basically, you know, in Cartesian coordinates, if I tell you, look, I got a x squared plus y squared equal to a squared. Okay. So for example, right? Okay. So in your head, you immediately know, okay, I'm talking about a circle here, right? So we should have a similar basically reaction. If I give you an expression in terms of a cylindrical coordinates, then you should establish a similar reaction is, okay, so that describes something, right? Just like if I give you a Cartesian expression, okay? So for example, right, let's look at this one here. This is a circle. However, in 3D case, right, if it's in 3D case, this is actually what? If I tell you this, in 3D, this is not a circle. It will represent, what kind of geometry would this represent? In 3D, cylinder, right? It's a cylinder. So you just have to elongate to both sides, okay? So you get a cylinder. So then if I replace x with r cosine theta, I replace y with r sine theta. So I will get r squared equal to a squared, which reduced to r equal to a. Okay, so which means the next time if I tell you, okay, look, I give you an object represented by r equal to a. So in your head, depending on the question, if this is a 2D question, then it's a circle, right? Jump into your head. But if this is a triple integral, then r equal to a, in your head, you should visualize as a cylinder. That makes sense? Right? That's basically my point, how you can establish the reflection when you look at an expression like R equal to A. And so this gives you a cylindrical surface. Okay. Now, sometimes then you probably have a combination. You will see, okay, R, for example, equal to 2, and then Z is between 1 and 4. Okay. Sometimes the question is described like this. So now you will see, okay, so this is a cylinder, and the Z is restricted between 1 and 4. So if you have to sketch that, then 1 is here, 4 is here. So you would draw a cylinder, right, restricted between Z is equal to 1 and 4. Okay. So this is the point I'm trying to make here, giving you an expression in cylindrical coordinates, right? What can you visualize it, right? Just like you do that using Cartesian coordinates. Okay. Now, there are other situations is that, for example, let's say theta equal to 45 degree, for example. Okay, so just telling you theta equal to 45 degree. So how would that actually be reflected in a 3D space? So if you say theta equal to 45 degree, what geometry is that? Right. So first you should start with the theta, right? What is theta? This is your theta definition. Right? You draw a reading line, and the corresponding angle corresponding to that reading line is theta. So theta 45, so this is approximately what I draw here, right? Equal to 45 degree. Okay. And then you should try to visualize it in 3D sense. So what do? Right? So when theta equal to 45 degree basically means R and Z, the other two variables, there's no constraint, right? So we're not putting any constraints on R and Z. So these two variables, they vary. They can vary to any numbers. So now you can in your head visualize. So what would theta equal to 45 degree produce? Anybody? Yes, a plane, right? So you would probably just elongate this line to the top and the bottom. Okay, so you got a plane, but I think in the textbook there's a little bit of mistake. If I would see it's a half plane, okay, so it doesn't include anything beyond that z-axis over there. It's just on this side of the z-axis. Okay, there's more of a half plane. If it's a full plane, then it's actually right back and forth to both sides, then you got a full plane separating the whole space into two halves. Right? So that's what theta equal to a constant would give it to you. And R equal to constant will give you that a cylinder. So similarly, and then you see, okay, what about a Z equal to constant? Right? If you see, I have a Z equal to constant value, meaning R and theta, they don't have any constraint, they can vary. Okay. So then Z equal to A, right? I think we have done this before, is basically, that's a plane, right? It's a flat plane at Z equal to A. So this is a plane. Okay, this is true plane, actually. So next, when we learn cylindrical coordinates, we're gonna have a similar, basically, expectation is that if an expression is given, okay, in spherical coordinates or cylindrical coordinates, you should be able to establish or visualize what this object actually looks like. Okay, yeah, that takes a little bit of time, okay, or training, but just like you're able to visualize an object using Cartesian, should be able to visualize using different set of a coordinate system. Okay. All right. So let's look at an example. Okay. I think this is an example I started, but I didn't get a chance to finish. Region D is given as z equal to x squared plus y squared, and then z equal to 4 minus x squared minus y squared. So we're able to sketch this region D, okay, because the two surfaces at here are fairly familiar to us. The first one z equal to x squared plus y squared, and that is a paraboloid pointing upward. And then z equal to 4 minus x squared minus y squared is a paraboloid pointing downward. And with the maximum value 4 over here. And then they intersect, right, at a certain place. Okay. So essentially, D, okay, is on the top is this surface, at the bottom is that this surface here. It's like two bows, okay, on top of each other. And let's say I'm interested to find out the volume of this region D. Right. So right now the integrand here is 1. So basically the function f is 1. If function f is 1, then the result of this triple integral give us is the volume of this region D. Right. So I will try to illustrate the Cartesian coordinates, but I'm not going to calculate because it will be very complicated to calculate this volume using a triple integral using Cartesian coordinates. But that doesn't stop us from setting it up using Cartesian. So let's see how it looks like if we set it up using Cartesian coordinates. Okay, choose the order. Let's choose the order dz. dz, dy, and dx. Okay. So if this is the order you choose, then look at the last two variables, which is x and y. And that basically means I need to sketch the shadow of this object in the xy plane. And that's pretty obvious. It's this geometry, right? If you project it into the xy plane. Okay. Now the question is basically, right, what will be an equation for the shadow? Okay, so that can be found based on the given two surfaces. So you have two surfaces here, and the shadow is basically the intersection curve. The intersection curve can be solved using the two equations. When they intersect, the z will be the same, right? At any one of the intersecting points, the z value is the same. So all you need to do is you need to let the two expressions equal to each other. Okay. And then you solve for x, y, move all the x, y into one side and simplify, and you get x squared plus y squared equal to 2. So this curve at here, or the shadow, is basically x squared plus y squared equal to 2. That's how you can get the shadow based on the intersection. The next step, right, once you get the shadow, and the next step is to follow the procedures of Cartesian coordinates, how to find the limits. So if you recall that, what you do is, within the shadow, pick a point, and then you draw an arrow line, okay, in the positive z-axis direction. Okay. The reason you draw it in the z-axis because you do it in z first, right? That's why we draw this arrow line in the z-axis direction. First contact give you the z mean, second contact give you the z max. Okay, so then I'm ready to set up this triple integral. So first it's dz, and then dy dx. So the integrand here is 1. Z mean is the bottom surface. Bottom surface is this. So it's x squared plus y squared. The top surface given by that, so that's 4 minus x squared minus y squared. Okay. So that's your Z mean and Z max limits. Okay, so next step is to find limits for Y and X. The limits for Y and X are based on shadow. So here's a shadow here, right? So since you're doing Y first, then you draw an arrow line across the shadow and in the Y-axis direction. First contact give you Y mean, second contact give you the Y max. So Y mean is at the bottom half of the circle, Y max is in the top half of the circle. And that is determined by the shadow equation. So Y mean is a negative number, Y max is a positive number, and not a number expression. So your expression here is negative 2 minus x squared to positive 2 minus x squared. Okay, that's your Y mean and Y max. Finally, you sweep this bottom arrow line from one end to the other end, one edge to the other edge. Find the edges, right, sandwiching this shadow. And that's basically from one end of the radius to another end of the radius. So this negative root 2 to positive root 2 because radius is root 2. So this is your setup for triple integral in Cartesian coordinates. You can certainly try to work it out, but I can guarantee that it will be very cumbersome to carry out this computation because of the square root terms here. So this is where we can explore a different method or different coordinate system, okay, to calculate this triple integral. So now let's take a look at in cylindrical coordinates how to calculate this triple integral here. Okay. So cylindricals are theta z, okay, and don't forget that x equal to r cosine theta, y equal to r sine theta, and z is still z. Okay. First, so step one, order. Again, we emphasize that the order for cylindrical, okay, most of the time you want it to this order, dz, dr, d theta. So of course, don't forget the r in front of this, right? So you do have r over here. And then second step. Okay. So sketch step is still you need to sketch the region D and the shadow in XY plane. Okay. The reason is we need this region to figure out the Z limits. We also need the shadow, which is XY plane, to figure out the R and the theta limits. Okay. So we already have the sketch, but just for this benefit, let's just resketch that. All right, so here is the actual region D and its shadow. Okay. Okay, so now the next step is to find limits. Okay. First is to find the Z limits. Okay. To find the Z limits, what we do here is actually exactly the same as what we do in Cartesian coordinates. So within the shadow, you draw an arrow line, okay, in the positive z-axis direction. Okay, then so basically you draw an arrow line in the positive z-axis direction. So, first contact gives z mean. The second contact gives z max. Okay, so Z mean is the bottom surface, which is x squared plus y squared, right? But you don't use x, y anymore, right? You're using cylindrical coordinates. So your x and y should be replaced, okay, with r cosine theta and r sine theta. And once you substitute into this, and it becomes pretty obvious, and you end up with just r squared, right? And then Z max is given by 4 minus x squared minus y squared. Okay, you do the same thing. You replace x and y with r cosine theta, r sine theta, and you end up with the 4 minus r squared. So that's your Z limits, right? So in terms of its own coordinate variable at r and theta. So now you got your Z limit, and then next step is to find r limits. The r and theta limits are based on the shadow, right, which is the circle at the bottom here. So this is x squared plus y squared equal to 2. Okay. Now, however, if you recall, right, we're not using x, y coordinates, so the circle at here is equivalent to r equal to root 2. Okay. And that's exactly what we have done in the beginning. You know, when you have r equal to root 2 is equivalent to x squared plus y equal to 2. Right? So then what we do is, right, as just like what we did for polar coordinates in double integral, you draw an arrow line, okay, in the reading direction, okay, in the xy plane. So first contact gave you r mean, second contact gave you the r max. So your r mean is 0, and your r max is root 2. So there's nothing tricky here, just like you did for double integral. And the last step, you're going to sweep this reading line across the whole shadow, which is the circle. You start from x-axis, you know, you rotate, okay, across the whole shadow. And the shadow here, if it's not a complete shadow, then you stop wherever it is. You're basically looking for edges, right? What are the edges that sandwich this shadow here? So in this case, you have a full circle here. So that edge, okay, will give you a 0 to 2 pi for theta angle. So rotate this reading line, right, across the shadow. So then you find theta mean is 0 and theta max is 2 pi. This is basically the end of your limits, right, for all 3 variables. So finally, you can set it up. 3 integrals. You're doing r, dz, dr, and d theta as the order. So r goes from, as we just find it here, for z goes from r squared to 4 minus r squared. And then r goes from 0 to root 2. And theta goes from 0 to 2 pi. Now this is a very simple integral to deal with, much simpler than the one we have demonstrated in the Cartesian coordinates. Right? So you're gonna get, so let's just do one more here. So this integral, right, for the dz, you got r times 4 minus r squared minus r squared, and then dr d theta. Okay. Right, so the result of this first integral with respect to the z give you this. And you got an r, don't forget the r there, that's the original r, right? Okay. So this integral has nothing to do with theta. So your theta basically will be 2 pi. So 2 pi might multiply by the results coming out of this integral here. So you're going to end up with just a 4 pi. Okay. Yeah. So I think you would prefer to use the cylindrical coordinates rather than the Cartesian coordinates for calculation of this question here. Okay. Now, this is actually doesn't necessarily look like a cylinder, right? The region here. So this is not sometimes not intuitively, would see, okay, I should use cylindrical coordinates rather than Cartesian coordinates. But now because the r and theta are determined by the shadow, so the rule of thumb is if the shadow of the region D actually is a circle, then chances are you can use these cylindrical coordinates. Okay, so that's the rule of thumb. Sometimes, if you see as we after learned the spherical coordinates, both the cylindrical spherical coordinate works. Both of them can work for a certain question, right? Okay, so let's look at another example here. So this example is not necessarily another example of a calculation, but let's start with, again, it's a reflection of what does this geometry or what does this expression give us? So if I give you an expression z equal to square root x squared plus y squared, okay? Now it's hard, if you don't have a computer software, you don't know what it actually looks like. But if you plot it, okay, you will see that this gives us a surface like a cone. Okay, it's a cone surface. So this one gave you a cone here. So I'm going to demonstrate basically what will this cone surface, which is in Cartesian coordinates as square root x squared plus y squared, what will it be if we transform it into cylindrical coordinates? Okay. Yeah. So let's express press the cone in cylindrical coordinates. So here's your original Cartesian. Okay, don't forget that. Okay. And transformation is very straightforward. All you need to do is you replace your x and y with r cosine theta and r sine theta. So let's see what does it become. So you get r cosine theta squared and r sine theta squared. Okay. R squared cosine theta squared plus r squared sine theta squared is root r squared, which is r. Okay. R itself is a naturally positive number because r is a distance from any point to the origin, right? It's positive. So that's why you don't need a positive negative here. Okay, so basically that expression is transformed into z equal to r, right? Okay, so then the question basically is the next time if you see an expression as z equal to r, okay, so your reflection is, look, this is actually a cone. Okay, there's a cone here. Now, in general, if you put a constant, okay, if you put a constant in front of that square root term, a here is constant. So in general, this is a cone. Okay, so that is this is a cone. Okay. So what does that basically A, right? What does the A do to the cone? Right? If let's say, given this example here, apparently here, right, A equal to 1, right? If you A equal to 1, you get that cone back, right? Okay. So here's what I want to show you at here, okay? I'm gonna just draw a line, okay, on the surface of the cone, starting from origin, and then you draw a reading line, okay, along the surface of the cone. And then I'm gonna, okay, pick a point anywhere, okay, on the z-axis, and then connect to that point over there. Okay, yeah. The nature of the cone is basically, right, if you slice the cone anywhere with a z equal to c, right, if you let the z equal to c, you get x squared plus y squared equal to c squared. So that cross section over there, right, is a circle. Okay, that's the nature of the cone, right? Then the triangle that we have just created at here. Okay, so if I'm gonna bring the triangle out of this cone here, so this is the triangle that I have just created. Okay, it's not very perfect, so I'm gonna just draw it here. Okay, yeah. And this is, of course, this is that 90-degree at here. Okay, and this distance at here. So technically, right, we know that's z because I picked a point here, an arbitrary point, right? So that's z. And this is r. Okay. So that's the nature of the triangle. And guess what? Right now, you have just derived z equal to r, right? Z equal to r. So basically means, how much angle is this? 45-degree. So let's call this angle phi at here. So that basically gives me a phi angle equal to 45-degree. So look at how this phi angle is created, right? We arbitrarily created a line, okay, and on the edge of the surface, a reading line on the edge of the surface, and based on this given cone. And we demonstrated that the phi angle equal to 45-degree. So basically, you can visualize in the next time, if I give you an expression, this is actually part of the spherical coordinates next, okay? If I tell you phi equal to 45-degree, what does this geometry look like? Now you can visualize in your head, it's basically a cone, right? Everywhere at 45-degree. So the next question basically is, what if, right, the coefficient at here is not 1, but some other different numbers. So essentially the A value is a different numbers. How does that change the geometry of the cone at here? Right, so let's take a look at this here. Let's say, for example, A equal to 1 over root 3. Okay, so let's use a different cone surface at here. So I get Z equal to 1 over root 3. X squared plus y squared. Okay, so for starters, you should absolutely certain this is a cone, right? Obviously, the angle will not be 45-degree anymore, right? It will be some other different angles. Let's find out. Is that a cone going to be a wider cone, or is it going to be actually a narrow cone, right? Yeah. So we do the exactly same approach. You replace x and y with r cosine, r sine. You will end up with 1 over root 3 times r. Okay, so that cone surface in cylindrical coordinates is z equal to 1 over root 3 times r. Okay, so if I do the same procedure, I'm going to create, okay, a triangle like that. Okay, then here's a z, here's r, okay, and here's a phi angle. Okay, so let's take a look at the relationship, right? So right now, the z and r is related by this expression, and here's a phi. So technically, and you have tangential phi equal to r over z, right? And you already have the ratio r over z. You have it over here, right? So r over z, the ratio is, what is the ratio between r over z? Root 3, yes, right? So tan phi equal to root 3. Use your trick knowledge, the phi angle has to be 60 degrees. So this is more than 45 now, right? So which means you change a from 1 to 1 over root 3, your cone is actually wider now. That makes sense? Yeah. So that's the effect of the A value, right, on this cone's surface at here. Okay, so the next time you go get an ice cream, then you want your ice cream, make sure the coefficient A there, right, is less than 1. Okay, so then you can get more ice cream in the cone there, right? So anyway, I guess the reflection, right? The reflection you want to establish is given a Cartesian expression, what is this corresponding cylindrical expression? And then you can tell immediately, given that expression, what kind of a geometry it actually describes in 3D space. Okay. So let's take a look at an application of cone surface, right, in triple integral here. Okay. So I'm going to integrate x squared plus y squared, okay, over certain region D. And region D is given by z equal to root x squared plus y squared, and then z equal to 4. Okay. So first step, you got to draw this region D out. And that is a cone, as we have already demonstrated. And then it has a top surface capped at z equal to 4. That's basically not an unlimited cone, right? So you have a cone with a top surface at z equal to 4. And then this is z equal to root x squared plus y squared. So we're integrating this triple integral over this region D. Obviously, you can choose Cartesian, you can choose cylindrical, right? You can try out the Cartesian, and I can guarantee it will be very complicated. So let's use cylindrical coordinates. If I use cylindrical coordinates, for order, right, is always, not always, but most of the time, 99% of the time, will be dz, dr, d theta. Okay, so then once you've done this order here, the next step is you draw the shadow, okay, in xy plane, because the shadow will determine your r and theta limits. Obviously, the shadow is just a circle on the top. And that will be the shadow. So then the question basically, what is the circle equation? Right? So that's completely based on the boundaries of the region D. Okay, so this is top circle is the intersection between z equal to 4 and z equal to root x squared plus y squared. So that basically means you let the two terms equal to each other, and then you get x squared plus y squared equal to 4 squared. So this is basically your shadow, right? It's a circle, it's a radius of 4. Now, once we've done these steps here, then you're ready to integrate this whole thing using cylindrical coordinates. Right, you can set it up. You're integrating x squared plus y squared. So we're going to have to replace x with r cosine, replace r with r sine. Right, so that's everything is converted to r theta z. So last step, to find the limits for each one of the cylindrical coordinates. First step, to find the limits for the z. So what do? Pick a point within the origin, then go up in the positive z-axis direction. First contact give you z mean, second contact give you the z max. So z mean falls on the surface of the cone. And this is where you actually will make use of the results, or if you don't have it, that's fine. You can still make use of the, you can calculate on the fly too, right? So the surface of the cone, as we have demonstrated, is z equal to r. Okay? So your z mean is actually r, and your max is on the top surface, which is 4. That's your z limits. The r limits, you draw a reading line out of the shadow. First contact r mean, second contact r max. The last step, you sweep this arrow line across the whole shadow to find the theta limits, which is theta 0 to 2 pi. So that completes this setup of this triple integral in cylindrical coordinates. So the rest of the calculation is actually fairly straightforward now. Over here, you got r squared times r, so it's r cubed. So I don't think there's any tricky things at here in terms of this. Okay, so I would encourage you to calculate this triple integral yourself. Okay. Actually, I don't have the answer for this, but you can calculate. So now you can see the sort of the bigger picture, right? For cylindrical coordinates, as I mentioned, if the region D's shadow in the XY plane involves a circle, then chances are cylindrical coordinates will work better than the Cartesian coordinates. Okay. The other thing is you had to convert everything into cylindrical coordinates. If a surface like a cone involved like this, so you probably want to convert that into the cylindrical coordinate first. Okay, then you can calculate the limits properly. Okay. All right. So any questions on this cylindrical coordinates? Okay. Yeah, I think it's pretty straightforward, right? You just had to be able to identify first. Again, I'm a little bit right. Oh, I still have a few minutes. So let's just get started. We can always come back next lecture. So one more coordinates, right, for triple integral is spherical coordinates. Okay? And this is new. We never have done this before. So let's take a look at what is spherical coordinates. The bottom line is, okay, no matter what coordinates, okay, you're bringing here, okay, or you are learning at here, coordinate basically means it's the minimum number of variables that you can use to describe the location of a point in 3D space, okay, or sometimes in 2D space. Okay. So just like Cartesian x, y, z, for spherical coordinates, what we do is we define 3 new variables. So the number 1, okay, you create, okay, a line between origin and point P, and we call that rho. Okay, so Greek letter rho. And then you also create an angle, okay, from the z-axis to OP. Okay, so this phi at here, they start from z-axis and rotate all the way to where the OP vector, OP line is, and that gives you the phi angle. And last variable, you project the point P into the XY plane, and you create that like the R, right, in cylindrical coordinates, and then here is your theta. So your point P can be described by these 3 variables, rho, phi, theta. And the 3 variable rho, phi, theta is what we call spherical coordinates. Okay, so what you have to be very clear, okay, is number one is how the phi angle is defined. So I want you to be crystal clear that the phi angle is the angle from z-axis, okay, to, so let's call this OP vector. So you cannot define the phi differently. Right? Otherwise, if you define differently, then we probably have to stick to a different convention. But right now, the convention phi is defined as this, right? From z-axis to wherever that OP line is. And just like a theta, same thing for theta, right? Is angle from x-axis, okay, to the OP's projection in XY plane. It's also considered, right? Just basically all the rotation is always considered when you have a counterclockwise, a positive. When you have a clockwise, it considers negative angle. Okay, that's your theta. And finally, the rho, okay, is the distance from origin to point P. So the definition of these three variables, okay, you need to be crystal clear. So otherwise, when you find the limits, right? If you use your own convention, then we're not on the same page, right? Yeah. Okay, so I'm going to stop here. So we'll look at how to calculate triple integral using spherical in the next lecture. Okay, thank you very much. Feel free to come over if you have any questions. By the way, we have a quiz this Friday. I think it's the same Friday and Saturday. It's set up. Now to save us a little bit of marking this time, we're going to use all multiple choice plus there's one open, you fill an answer kind of question, right? Yeah. The format is still the same. It's free everything, open everything. Yeah.
There's a way to open my last quiz. So I was pretty unhappy with my.
Oh, okay, sure. Yeah. So let's disconnect this first.
My understanding of that topic, I felt with it.
Yeah. What did you get?
15 out of 24.
Oh, okay.
Which isn't obviously too bad, but I feel like my understanding is a little bit higher than that.